systems. So really it's about the work we have done, are doing, and will do in this. So the agenda is going to be just a very quick refresher on the programming model and the architecture and how it actually fits onto the NIC. Then I'm going to give a brief 2 minutes quickly on the performance we're seeing today and the optimizations we're going to be doing in the future. That's just to give you an idea of kind of how this fits together. And then beyond that, we're actually going to go on to the stuff we really need to do to be able to use this in production. And that's mainly what Jakob will be covering. So the programming model, and this has actually changed very recently slightly, and Jakob will go through those changes, but for now, this is the model as was. So really you compile your programs, you run your programs as you would do if it was not offloaded, and everything runs as per normal until you get down to the verifier. Once you get down to the verifier, we run it as normal, and then go down into the driver, where we can detect if you actually want to offload the program. So this is done via IP route, or if you're using CLS BPF, you can do it via TC. And at that point, we then rerun the verifier and have a few extra checks which we use for the JIT and for the actual offload. So there are a few things like, for example, if you've got a map type we don't yet support, in which case we won't actually offload the program, and then you just run it in the driver as per normal. So really the idea is to give you the offload if you want it and not if you don't. Next one. So this is just, and I apologize, it seems that our slides are cutting off at the side, but what this is about is this is to show just how it fits onto the actual NIC. So you've got your 10 BPF registers, they go into our general purpose registers. We have about 64 of those per thread, and you've got 60 cores on the device. So, and 4 threads per core running. So there's actually 8 threads, but we only use 4 for our BPF offload at the moment. And then you put the stack into the local memory where we have about 1 kilobyte per thread on each core. And then at the moment, the maps of all sizes go down actually into DRAM. So we have about 2 gig of DRAM there. We can actually hold up to 8 gig of DRAM there on the NIC if we want to through the chip. And we have a bunch of other memories which we don't actually use at this point in time, but they become important later on. So this is just to give you a quick example of performance we're seeing. So I quickly hacked up a simple XDP load balancer. It came to about 800 BPF instructions, and there were 4 lookups. It's based on the TC example in the kernel, which you can find in self-test BPF L4LB.c. And then I just combined it with the IP tunneling from XDP TX IP tunnel to create a very simple load balancer. It's not optimized, big health warning, this is not perfect. The one change I had to make to offload it was there's a per CPU array for the stats. I had to change that to a standard array because we don't quite hold the actual per CPU system. Doesn't really make sense for us at the moment. We would have to put a small map in every single core, which would be unideal at this point in time. So we can do that in the future, but at the moment that's not something we're doing. So I ran it as is today with the offload as we have it in our POC at the moment. And we got to about 24 million packets per second. In the driver, it ran at about 21 million packets per second, which was about 2.6 million packets per second per core. So you're getting a lot from the offload. And then what I did was a few of the maps are quite small. So at the moment, as you saw from the first slide, we put all the maps into DRAM. Now, if you actually take the smaller maps and you put them higher up, so you use the memories which are much closer to the cores, then we were getting this running up to about 42, 43 million packets per second. It's just a rough number. It's just to give you an idea of where we stand today. And there's still a lot of optimization left to do. So at the moment, the map placements can be improved. I put caching there, but really you can't really use caching if you're doing things like DOS. So it's really about the placement. And then what I've called the packet cacher is we actually have a store of the packet on the core in each thread as it's running, but we're not actually using that today. Today, when any packet access we do, we're actually going to a piece of memory which is on the island, which is about 50 cycles away, even though we actually have a packet sitting 3 cycles away. Now that's because it was easier to do and it was quick to get done. Now that's an optimization we have in the future. And Jong, who's in the audience, has been doing a lot of work on 32-bit ALUs for LLVM. And that obviously then also is significantly better when you have a 32-bit architecture like we have, because it massively reduces the amount of instructions you're actually using. And finally, there's some firmware locks which we can get rid of. But the important thing and what we really want to focus on today and what we want to focus on in this talk is about how we get ready to use this in production. how you can use this and how you can feel safe and comfortable when you're running it in a, in a massive data center. So the first thing we have is, and this I'll briefly touch on, is multi-stage processing, but we've called it here. But what that really means is that there could be situations where you've got a huge chunk of BPF programs running and you don't want to run all of them in the offload mode. You actually want to offload some of them and run some of them in the driver. That could be for a variety of reasons. You could have new features which haven't yet been implemented in the offload, which are running in the driver. There could be many other things going on like that. Or you could have, you could have maps which are 20, 30 gig in size. I don't know, you could have something funny going on like that. So there's some reasons why you would want to run some of the programs locally and others remotely or offload. And then obviously we'll talk about the debug work. And finally, we'll mention about the JIT architecture and the changes we've made, whereby the verifier now reruns in a different place. So effectively you rerun the verifier much earlier. That's before you have a lot of the optimization for the host architecture happening, which means it's much easier to offload, and it means we can keep feature parity much quicker. So just quickly, I'll touch on the multi-stage processing before handing over. We can obviously, the edge case you run into here is what if you have tail calls which are going to different programs. You have some programs leaving the NIC, having done, let's say, 3 or 4 BPF programs, that want to then go to a particular other BPF program, whereas some of the other examples could tail call into a different BPF program. So you could use something like the XDP, the data meta fields, which Daniel Borkman added, to make sure that you actually go to the correct next program. It's just a very simple thing which you need to be able to handle, I think, once you get to the stage of using this in anger, really. So I think that's pretty much it from me. At this stage, I'll hand over to Jakob, who will talk about most of the real work we're doing.
Thank you. So updates, we gave a presentation about the same subject a year ago, and I will go through the items and what we've been doing for the last year. So things we changed upstream. There were some instructions that Daniel added for comparisons, so he was nice enough to implement them for RGs as well. Jiang has added a negation instruction, and I've added a byte swap and I think some others. So that just, I think we are pretty much covering the basic instruction set for BPF, or at least what LLVM is using. We also added direct packet access, so which is the newer way of accessing packet data in eBPF, so based on packet pointers directly. So that's supported. It required some verifier changes and basically sparked their decision to change our architecture slightly. I will talk about that more in detail later. We also have full stack support, all 500 bytes. I think pretty much anything that the verifier will accept we can offload. So unaligned accesses, yes, pretty much anything. I put the adjust head helper here. We don't have that upstream yet. I was hoping I would be able to post the patches during the week, but I wasn't. But that's all ready. So we will be able to support adjust head, perhaps in the next merge window, but yeah, hopefully soon. And as Nick mentioned, Jiang has added a basic 32-bit subregister support to LLVM, and we'll be continuing the work both in the kernel, LLVM, and basically all the toolchains. And there's a whole bunch of stuff that we have prototyped and implemented internally to test the performance and see where our bottlenecks are, and also to just get a feel of how this stuff all fits together. And I don't think we will be upstreaming it in the form that it is today, because there's a lot of sharp edges. But we do have map offload basically running, and Nick was showing the performance numbers for the implementation. And we have atomic operations as well, so the atomic add that the eBPF can support. We have other atomic operations, but well, we can expose them in the instruction set if people need them. But right, the chip can do more atomic operations than just add. Also, Nick mentioned the optimization, so yeah, I will talk about this in detail slightly, because it would require some APIs perhaps to be added to the kernel. But the Jiang has started working on some optimization in our JIT, and those optimizations will probably become more and more complex. So the ones that we have right now is we have some that are very simple, which are already upstream. But there are the latest one was memcopy optimization. That's not yet posted upstream. But basically, there are no loops in BPF right now. So mem copies are completely unrolled, and that generates slightly unoptimal I/O pattern for us. So Junk has added optimization to basically roll them back into a single big I/O operation. And yes, the work on register tracking basically comes down to trying to make sure that if there's a 32-bit value kept by the register, we don't have to do 64-bit ALU operations on them. So save some cycles and code space there. The bigger changes that we have contributed are mostly about tooling. Obviously, when you start implementing a more complex project, you need to think about tooling. And one of the first things that we needed is a way of performing map operations in like a flexible and easy way. If you look at the BPF samples that are in the kernel, they're basically all BPF programs today have sort of two elements to them: the control plane and the data plane. So eBPF is the data plane, but there's also a control plane program that understands how the BPF program works and communicates with it through the maps. And that's how it's usually deployed, but for testing purposes and for just introspection into seeing what's running on the system, it's useful to be able to just perform like single operations like map updates and lookups by hand from command line. So we added the BPF tool, and it's in the kernel tree, and will be in the 4.15 release. It's also on GitHub, but we will probably remove it from GitHub because the int3 version is more up to date. And it basically allows to list and read information about all the BPF objects on the system. So all the stuff that the kernel exposes. This basically leverages the work that Martin from Facebook did to expose all the BPF information and some of the old stuff that was already there in the file descriptor info, and that gathers them in one place that's easy for people to access. And it also allows the dumping the JITed images, the host JITed images, and just the BPF instructions and printing them. And as I said, all the map operations. Yes, and recently Quentin also added the JSON output, which is extremely useful for us for testing, hopefully for other people as well. And there is some BPF FS integration also that Quentin did, and we had patches from Prashant lately, which was very nice to see someone else, someone from outside the company contributing to the tool already. So another piece of tooling that we really needed and have put upstream is the Junk's work on LLVM machine code. That's basically an LLVM macro assembler. And we started writing the tests. Basically, if writing the hardware translator, we have a need to test particular BPF snippets, like sequences of instructions. And the way that the test infrastructure in the kernel does it today is basically they include the instructions inside the C program, and there are like a static array of instructions. But that's not great for testing and for adding test cases. So we added the LLVM MC. So basically right now we can just write the BPF programs in the same format as the verifier uses for logging its log output, and assemble that into ELF files and load that directly. So that's really useful for us. And that also will be useful if someone wants to add inline assembly to BPF C code in LLVM. We are probably not going to be too interested in this ourselves, but it opens the way to implement that. So now into the kernel changes. This is how the BPF offload sort of worked until recently. And you can see on the left-hand side is the BPF subsystem interactions, and on the right is the networking stuff. And one thing that I should point out from the start is that there's no lines crossing from the one to the other. So BPF programs are loaded and verified and basically prepared. And then there's another system call which is attaching them to a specific place in the kernel. So when the user wants to load the program, everything is done by the BPF subsystem, but if we want to offload that program later for the network device, there is no way for us to know that at the time of the first verification, and basically a lot of information is lost or things are changed, and that makes the offload more challenging. So this is the way that we used to work. When the BPF program was attached to and the driver was informed either through the TC NDO or in XDP that there will be an offload, we would try to reuse the BPF infrastructure and sort of pretend that we're loading the program for the second time, and basically rerun the entire load part of the verification, and that would allow us to gather information and then JIT the image, JIT the program into the hardware. But as I said, when we start adding more advanced features, this becomes problematic. And the reason is, as I said, there is no information for which device the program is loaded, and a big problem is that the verifier, when the program is loaded, will actually modify it. So after the program is loaded, the original image that the user has loaded is completely lost, and we sort of have to make reverse the modifications to offload it. So what we have done is right now we have hooked the driver offload stuff directly into the first invocation of the BPF program loading. When users are loading the program, they can optionally specify the device index, the Netdev index for which the program will be loaded, and then the BPF system call will find that net device and basically inform it about the program as it goes through the verification and the JITting stages. And that all will be done before the modifications take place. So basically, the load system call will be invoked, and the appropriate netdev is found and bound to the program, and the driver is then informed about the program being loaded for it. It can prepare all its all its data structures for the translation. And then on every stage of the verification, it will get a callback with the current state, so it can learn about what the state of the program is as it is executed. And when the JIT happens, we will not perform the JIT for the host. We will again just call the driver, and the driver will generate the image that will be useful for the device, and that this program will not be executed on the host effectively. And this also allows us to inform the BPF core, place some of the offload state inside the BPF program structure, which makes it easier to later report state, makes it more natural to report state about the offload of the program without having to go through the Netdev infrastructure. The BPF core basically already has all the information it may want to report. So, to go again through the challenges and why we changed the model in more detail. The modifications, the first item is the modifications that are performed by the verifier. It changes the offsets of the field offsets from the ones that are exposed to user space to the actual kernel structure offsets, and that's slightly easy to reverse, although not entirely clean as far as the implementation goes. The second problem is the functions. So when the program is loaded from user space, the functions are referred to by IDs, and after the first verification, the verifier will patch them and change the instructions to contain basically pointers. And the third problem is with the maps. So when the program is loaded, the map pointer load instructions are specially marked, and that those markings are removed by the verifier. So if we want to offload the program to a device, we need to basically find all the map references, and it's kind of impossible to find the pointer loads when the markings are already removed. Another thing that happens after the first verification is there may be a prologue or epilogue generated for the program, which either populates some information or does some extra checking, which basically again generates some code which the verifier will not be able to parse the second time around. So that is basically a showstopper. So some features like direct packet access for write would not be possible to offload in the previous architecture. And there are optimizations that the verifier does, and I think today there's only one. Alexei added inlining of lookup map lookup calls. And again, when the program is loaded from user space, the map lookup call is just a call, and I think ID1. But the verifier will inline some of the code. Basically, the invocation of the map lookup is sort of an indirect call. The first helper just does basic checking and then calls the actual implementation for the given map type, so that the basic checks can be inlined, and then we save one dereference, basically one call in direction. And that's great for host performance, but for the device, it's neither useful nor is it possible to get that through the verifier for the second time. And the other problem is when we load the program onto the device, there is really no flexible way to report errors. And the verifier log, as much as some people may say it's deficient, it's actually quite useful and flexible to just output errors or information basically as we translate or as we verify the program. And this could be just errors, like just telling the users why the program couldn't be loaded or offloaded, or just state about optimizations which were done or not done for some reason. So the verifier log is a really useful tool, but obviously if we run the verification for the second time inside the networking subsystem, there's no way for us to report it back to user space. So moving the translation for the device to the load stage is really useful in that regard. As I said, also the BPFs, we can now place some of the state inside the BPF program structure itself. So we are hoping to report the translated image. So basically, when we translate the program for the device, we are actually generating machine code. It's not like some abstract instructions that the firmware will then translate to something else. It's the actual NFP machine code, and we can take that and disassemble that with some libraries. So we are hoping to be able to dump those images, those translated images, back to user space, and perhaps extend BPF tool to be able to disassemble NFP code, so users can see what the BPF programs were translated on the hardware to, the same way they would be able to for x86. And that should work pretty naturally in the new model. The only thing we need to add is the machine type effectively, because if we are talking about the JITed image for the host, it's obvious that which disassembler to use. Basically, the host disassembler is the correct one, and we can easily find out what the host we are running on is. But if it's an offload device and it's an NFP or an ARM core or whatever else, we have to include in the user space, in the program information structure, which machine type the image was generated for. And another extension which we will hopefully add soon is there's a lot of places where the extended acts were added in the stack already, but the TC offloads have been left out for now, and we will hope to extend that hopefully soon. We have already the X stack in XDP callback, in the XDP NDO, but having it in the setup TC one would be extremely useful as well. We can actually, we know ourselves that this is a very powerful tool, and the number of questions I've got asked about why my XDP program does not load fell dramatically after I implemented this, so I really like this, and we'll implement this for TC as well soon. Another thing that is still missing for other people for basically production readiness is being able to report information when the program runs on the hardware. So I think everybody who uses BPF programs today uses some form of print K or the perf event output to basically trace what happens to the packet as it goes through the BPF program. And we have the implementation of perf event output in the firmware, but we need to bring it out, basically supported in the driver as well. And yes, as I said, the optimizations that we do in the driver are becoming more and more complicated and more complex, and obviously with complexity there might be some bugs which lurk in, and also if we start optimizing the programs in non-trivial ways, we may change how the program works. We don't intend to break the BPF API, but obviously as we do optimizations, things may start working slightly differently. on the host and done on the host, and until we change or fix the optimization, it would be great if we had a way of like disabling particular optimizations that we have in the driver. And that will actually be useful for the host as well. Right now, the inlining optimizations is keyed on basically JITting the program, and perhaps there would be some use in being able to control that as well for a separate API instead of just like using the JIT flag. And last but not least, I showed the way that we change the architecture for programs. We don't have map offload, but we are actually thinking about doing a similar thing for maps. So instead of offloading the maps when they get attached to a device, create the maps from the start on the device itself. And the reasoning for that is effectively exactly the same as for the program, where there is no verifier to go through, but error reporting gets a lot more easier when the error can be reported when the map is created instead of when the program is attached to the device. And the complexity, there is some complexity in the process that it takes to take a map that exists in the kernel and can be accessed from user space already and put it on the device. We need to basically stall all the map operations and offload the map fully and then allow the operations again. It's not very hard, but it's perhaps unnecessary complexity if most people will just want to offload the map from the start. And there's also some trickiness around around claiming the maps, because we want to support the use case where there's two programs effectively reuse the same map, because for instance we want to offload both of them onto the same device or replace one by the other, but we can't really allow programs that won't be offloaded to claim the same maps as those which were offloaded. So there is some complexity, and the maps also don't contain back pointers to the programs to which they are bound, so it will simplify things if we just create the maps on the device from the start. And that's basically it. We will. If there are any questions?